Today on How It's Made. Bicycle helmets. Safety first, second and third. Aluminium, making the most versatile metal around. Car brakes, from anti-skid to ABS in 4 minutes flat. And lithium batteries, revolutionising the power pack. But first, if you're serious about bike riding, you should also be serious about safety. And it all starts with your head. Today's bike helmets meet all the required safety standards and come in a wide range of colours and styles, which means you can protect your head and look great doing it. Allegedly. A bike helmet is constructed of an exterior shell and an interior one made of polystyrene foam, designed to absorb shocks. When designing a helmet, artists take into account that for the safety helmet to be accepted by its younger users, it must also look stylish. Fabrication begins with the exterior shell. This polymer sheet is heated in a heat former at a temperature of 65 degrees centigrade. The sheet is suction fitted to fill all the cavities of the mould. This operation produces 4 shells. Then, when cooled down and hardened, the 4 shells are cut by hand. Ventilation openings are cut with a heated wire. These openings have been pre-formed during moulding of the shell. The heated wire easily and neatly cuts the polymer. The next step is the trimming of the helmet to eliminate excess polymer. The circumference is manually cut using a router. The edges are then sanded to even them out. It's also possible to cut the circumference of the shell with a heated wire. This operation takes more time, but is much more precise because of the resulting cleaner cut. The foam interior of the helmet that will be placed inside the shell is made of polystyrene beads that will expand and bond together. This expander increases the volume of the granules that fall into it. Steam and an agitator force the polystyrene beads to expand uniformly. The granules are now ready. The contents of this bin will be able to produce about 20 foam pieces, which will take shape on moulds. The press closes up for 6 minutes. The particles are steam fused before being cooled with water. The foam is removed from the mould. Different designs are produced for different helmets. Depending on the helmet model, openings have to be made with this heat iron to allow for installation of an air vent. All that remains is to make the adjustment pads, cut with this press-powered stamper. The adjustments are held in with Velcro to allow easy adjustment of the helmet. Inserting the straps calls for good manual dexterity and takes only a minute. The shell and the polystyrene foam liner have to be joined. They're fitted one inside the other, then solidly secured. The helmet is now complete. And now it's on to packaging. The safety helmets have to be certified, guaranteeing their safety. Destructive tests are carried out on at least one helmet in 500. This facility can produce up to 4,000 helmets daily, in hundreds of models and over 500 variations. But whatever the design, safety helmets are a must every time we get on our bike. Take a look around and you'll find this wonder metal everywhere, from screen doors to jet planes. Aluminium has so many applications because it's light, strong, and corrosion and crack resistant. Producing aluminium may be costly, but it's worth it in the end. Aluminium is the world's most abundant metallic element, but it does not occur in a natural state. The main ingredient of aluminium is bauxite ore. The science of creating aluminium is simple. Atoms in bauxite are bonded to oxygen molecules. These bonds have to be broken by electrolysis to produce pure aluminium. Bauxite is carried by rail to a plant where it will be crushed. Then, through a chemical transformation called the Bayer process, alumina is extracted. This is then roasted to eliminate all moisture. This place is called the reduction facility. The plant has 432 pots in which a powerful electric current will be passed to produce electrolysis. An overhead crane dumps alumina into the pots. Then an electric current passes through it. It takes searing temperatures of 950 degrees centigrade to transform the alumina. But the electrodes which supply the electricity suffer in this heat. Each electrode has a lifespan of only 20 days. Spent electrodes are recovered from the pot with this overhead crane and carried off to be recycled. They clean the rods, which will then be reused. When the electrodes are replaced, the accumulated impurities that form as a crust have to be recovered from the top of the pots. This is done with pincers. Then a new electrode is inserted into the alumina and electrolysis continues. The electric current breaks the molecular bonds. The heavy aluminium collects at the bottom of the pot, while the oxygen is released as a gas, which is drawn off and treated. The liquefied aluminium remains at the bottom of the pot. It has to be recovered in this huge crucible with a tube. A vacuum system draws the molten aluminium from the crucible. Air is vacuumed from the crucible by a flexible pipe held by an operator. The tube is finally withdrawn and the overhead crane dumps another quantity of alumina into the pot. On and on in a continual flow, the aluminium continues to be created. The crucibles filled with their molten load are transported to the casting house. Their contents are poured into holding furnaces, which have a capacity of 60 tons. Finally, casting begins. The aluminium is either vertically cast, producing ingots or sheets, or directly cast into molds for finishing later. The cooling of aluminium pieces is accelerated by water sprays. The large rectangular ingots, which can weigh up to 25 tons, will head for hot rolling, eventually leading to products such as aluminium foil. 5 tons of bauxite have produced 2 tons of alumina, which in turn produces 1 ton of aluminium. This particular plant produces 200,000 tons a year. It's metalwork on a giant scale and feeds the ever-ravenous world with aluminium. Coming up in How It's Made. Car brakes, from anti-skid to ABS. Join us as we go from prototype to final design in 4 minutes flat. And lithium batteries, revolutionising the power pack and bringing the green car just a little closer. See you after the break. Welcome back to How It's Made. Later, we look at lithium batteries, revolutionising the power pack and bringing the green car just a little bit closer. But first, if you've ever had to stop suddenly while driving at high speed, you'll know that once you hit the brakes, the wheels can easily lock and the car lose control. But with sophisticated computer technology behind today's anti-lock brakes, skidding is becoming a thing of the past. Brakes have remained practically unchanged for the past 40 years. Conventional brakes have pads which press against the disc. These pads grip only a small area of the disc. This causes high temperatures, wheel skidding, and results in premature wear. The new floating disc brakes have 2 pads of friction material on 360 degrees of the disc's circumference. When the brake is applied, hydraulic pressure activates the diaphragm, which applies pressure on the pad, which is then pressed against the disc. However simple, the design of this brake called for a complex development. It all starts with a computer-aided design that has powerful software creating a virtual world of 3D images. The digital analysis submits virtual models to repeated braking to verify that the parts conform to design objectives. The software verifies changes in heat, the effects of vibration and resistance to breakage. The right choice of materials is critical. The electrical components also have to be created. Here, tiny sensors are delicately constructed which measure the force exerted by the braking system. The sensor is the main component of the intelligent ABS braking system, which functions more efficiently than traditional anti-skid systems and reduces braking distance. Then it's the fabrication stage of the prototype parts which will be tested. The machining of these parts must take into account the requirements of mass production. This high-precision machining is controlled by computerized digital lathes. A continual cascade of lubrication keeps the operation cool. The finished parts are precisely measured, then fitted and assembled to form the braking system, which will now be tested in the laboratory. These brakes have a friction surface 6 times superior to traditional brakes. The use of aluminium and composite materials allows for a weight saving of 2.5 kilos per wheel. They proceed to power and endurance tests on this dynamometer, in which a brake and wheel assembly act against the large rotating drum. These lab tests are critical, since they can detect any defect in a braking system before it's installed on the actual vehicle. To evaluate the power and endurance of the brakes in full application under extreme conditions, they're installed on a Porsche 911 Turbo, then entered in a competitive race. They proved effective, helping the Porsche to record many wins. Once all the tests are done, they move on to the next step. The brakes are installed on a production vehicle. With data systems reading everything, engineers can observe the performance of brakes under all conditions, thousands of times a second. Finally, engineers proceed with actual braking trials. Once these final tests have been approved, the braking system is ready to go into production. And that's the story of brakes, from original idea to final product. There's nothing like the sound of a car engine starting, especially when it's 15 below on a winter morning. Today's car batteries are smaller, more powerful and efficient, even at extreme temperatures. It's all thanks to the power of lithium-ion cell technology. While dissecting a frog in 1786, the Italian Galvani noted that when iron and brass were applied to frogs' legs, they caused the muscle to twitch. Later, Volta believed the current was produced by the metal instruments. To prove it, he stacked discs of zinc and copper connected by conductors and fabric impregnated with an acid solution. And so, in 1800, the electric battery was born. Batteries power all kinds of electric motors. A new lithium metal polymer battery pack such as this one could soon power an electric car. To make these new power units, you need lithium ingots weighing around 5 kilos. This ingot is transformed into a thin sheet by this extrusion press that applies 400 tons of pressure. The sheet has to be further thinned. Placed on a roller, it's carried to the laminator. At room temperature, it's thinned once again. In just 20 minutes, the 5-kilo ingot will have been transformed into a thin sheet 200 meters in length. This laminator completes the thinning of the sheet to between 20 and 40 microns. The resulting 2-kilometer-long sheet will go into making 210 battery units. Lithium is a soft, sticky metal. For this reason, a polypropylene film has to be fixed onto the lithium sheet. Without this protection, the sheet would adhere to itself and become unusable. The sheet will be used to make individual battery cells. These cells will then be assembled in series and inserted into battery modules. To make an individual battery cell, the sheet has to be rolled up. This automated spooling machine winds up the lithium film in 26 revolutions. The wound-up sheet is put into a vacuum oven, where the various layers adhere firmly to one another. This step lasts for about 90 minutes at 80 degrees centigrade. Here, a test is made. Using a voltmeter, the battery is checked to see that it produces the required 3.56 volts. A final quality check is made with this caliper, which precisely measures the thickness of the battery cell. One more step remains. The battery cells are to take a very hot shower. Metal is added to the mix in a procedure known as metallizing. The battery cells go into a protective tank. Then the metallizing of the contacts is carried out by spraying on molten metal. This takes just a few seconds, since the metal cools very quickly. The battery is now finished. It comprises 4 elements: lithium, which acts as the anode, a metal oxide cathode, a dry solid polymer electrolyte, and a metal current collector. All that remains to be done is the assembling of the individual battery cells into a module. It begins with the placing of individual cells onto one another and isolating them with foam. These red sheets are actually heating elements, since the lithium metal polymer cells function at temperatures of between 40 and 80 degrees centigrade. This unit is a battery pack for a prototype vehicle, a car that works with a petrol-powered and electric motor. And this battery was created for a totally electric vehicle. The true electric car just got a little bit closer.